Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 11-4 homework solutions on finding sums of infinite geometric series. To find the sum of this infinite geometric series, let's find our a sub 1 and our r value first. So a sub 1, that's going to be what I get when I plug the lower limit, which in this case is 1, in for n. 1/5 to the 1 minus 1, or 1/5 to the 0 is just 1. So 8 times 1 gives us 8 for the a1. The r is the term that's being repeated with multiplication over and over again. That's this 1/5 that's being raised to an nth power. Since r is less than 1, at least the absolute value is less than 1, which we always have to check, that means this does have a finite sum, so we can keep going with our formula. That formula, again, is a sub 1 over 1 minus r for an infinite geometric sum. a1 is 8. R is 1/5, so we have 8 over 1 minus 1/5. That's going to be 8 over 4/5. And then if I same change flip this thing, I've got 8 times 5/4. 8 times 5 is 40, divided by 4 gives us 10. To find the sum of this infinite geometric series, let's first figure out the a1 and the r. a1 is just our first term, 1/2. And then for the r value, I have to divide one term by the term before it to figure that out, what I'm multiplying by each time. So we can do negative 5/3 divided by 1/2. This is the same as negative 5/3 times 2 over 1. So that's going to be negative 10 over 3 for the r value. Now the absolute value of this positive 10/3, that's bigger than or equal to 1. So that means that since this is bigger than 1, this has no finite sum, and we can't keep going, we're just done. For this problem, to find the sum of the series, let's start by figuring out a1 and r. For a sub 1, we've got whatever we end up with when we plug 1, the lower limit of summation, in for n. If I do that, that turns this 2/3 into a 2/3 to the 0 power, which is just 1. So all that's left in that case is the 5/4. So there's our a1. R is going to be the exponential base that I keep multiplying by over and over again. So that's this 2/3 right here. And since that's less than or equal to 1, or just less than 1 actually, the absolute value is strictly less than 1, that means that this does have a finite sum. So let's do our formula. That's a1 over 1 minus r. So 5/4 over 1 minus 2/3. So 5/4 over 1/3. And then if I same change flip this thing, I've got 5/4 times 3 over 1. So this will be 15 over 4 for my final answer. To find the sum of this infinite series, let's figure out the a1 and the r. For a1, pretty easy. We've just got this 1 that we're starting the series with. For r, it's whatever I keep multiplying by to get the next term. Well, negative 3/4 divided by 1 is just negative 3/4, so also fairly straightforward. Now, we got to check here. The absolute value of negative 3/4, positive 3/4, that is less than 1. So that tells us that we are going to have a finite sum here. Let's plug that into our formula, a1 over 1 minus r. So we've got 1 over 1 minus negative 3/4, so we got to be careful here. This is going to be 1 over 1 plus 3/4 when we actually go ahead and do that. So let's see here. 1 is really the same as 4/4. 4/4 plus 3/4 is 7/4 down there. And then if I same change flip this, I've got 1 times 4/7, which is just 4/7. For this problem, I want the sum of this infinite geometric series. So let's find our a1 and our r to start this off. a1 is this first term of 24. R is what I have to keep multiplying by. So if I do negative 12 divided by 24, that'll tell me. And that's going to be negative 1/2. And you could do any of these divided by the term before it. It comes out the same. Negative 1/2, the absolute value of that is less than 1. This tells us that we've got a finite sum for this series. So we'll use our formula, S equals a1 over 1 minus r. So that's 24 over 1 minus negative 1/2. So 1 plus 1/2 then. 1 plus 1/2 is 3/2. And then if I same change flip this thing, so 24 times 2/3. 24 divided by 3 is 8. 8 times 2 is 16. To find the sum of this series, let's find the a1 and the r. For a1, when I plug the lower limit 1 in for n, I get 7/2 to the 0 power, which is just 1. For the r value, that's this exponential term that keeps getting repeated by multiplying, so 7/2. Now 7/2, the absolute value of that is greater than or equal to 1. So that tells us that there is no finite sum. This thing is just going to keep growing and growing and growing to infinity. For this word problem, we have a tire swing that we're pushing one time and then allowing it to swing freely. On the first swing, it travels 14 feet, and each time after that, it travels 75% of the distance from the last swing. We want to know the total distance this tire travels. Well, since we keep multiplying by the same thing over and over again with this 75% of business, that makes this a geometric series, an infinite geometric series, or at least close enough that we can use some infinite math. So we're going to go ahead and use our formula in a minute. But for that, we're going to need the a sub 1 and the r. So a1 in this case is going to be our initial amount of distance traveled. That's this 14 right here. R is what we have to keep multiplying by each time to get the distance of the next swing. So if we're traveling 75% of the distance from the previous swing, then that means we're multiplying by 0.75 or 3/4, however you want to express that. And then it is worth noting that 0.75 is less than 1, the absolute value of that's less than 1. So we will get a finite sum that means we're allowed to use our formula. So let's go ahead and use that. We've got a1 over 1 minus r. So 14 over 1 minus 0.75. This is 14 over 0.25. Now we could use the calculator, but this is like dividing 14 by 1/4, which same change flip is like multiplying 14 by 4 over 1, and that comes out to 56. So 56 feet for this answer. For the next couple problems, we're trying to write a repeating decimal as a fraction in simplest form. And we're going to do that by first expressing each of our decimals as an infinite geometric series. So for this one, for example, we can do 0.2 plus 0.02 plus, to get this next 2, we would need to add 0.002. So we're basically deconstructing this thing. So if this is an infinite geometric series, I can get my a1 and my r out of this. a1 is the 0.2 in the beginning. And for the r value, we can do 0.02 divided by 0.2. So this is basically like having 2 over 20, which is 1/10, so 0.1. Since 0.1 is less than 1, I do have a finite sum for this, and I can use my formula. So we have a1 over 1 minus r. In this case, that's 0.2 over 1 minus 0.1. So 0.2 over 0.9. And then if I just move the decimal for each of those, that becomes 2/9. To write this repeating decimal as a fraction, let me first turn this into an infinite geometric series. So I can write 0.16 plus 0.0016 plus 0.000016. There we go. Whatever I need to get that repeating decimal going on. So I've got an a1 value of 0.16. For the r value, I can do 0.0016 divided by 0.16. And what does this reduce to? Let me just do this on the calculator. So let's see, hold on a sec. There we go, 0.0016, too many zeros, divided by 0.16, and that comes out to 0.01, which makes sense. We just keep multiplying by 0.01, so we just keep moving that decimal backwards, left 2 spaces. So there's our r value. So because that's less than 1, I definitely have a finite sum for this thing. Let me go ahead and put that all in my formula. So we have a1 over 1 minus r. So 0.16 over 1 minus 0.01. This is 0.16 over 0.99. I can multiply both of these by 100 to move that decimal. So this is going to become 16 over 99. And there's no common factors between 16 and 99, so this is as good as it gets.